Can everyone hear me clearly? Okay, sawa sawa. So so this week we'll cover another topic, models computation. So we'll cover it in 2 bits. So the first bit we'll cover it today, then the second bit we'll cover it on Thursday. So for this week, we won't have a case study. I think we'll do one next week. Today's class is going to be a little bit not that easy, so I need you guys to pay attention. I want to make it a little bit, so that's why I've broken it into 2, so that we cover a few things, because they're going to be a little bit maybe difficult to understand for some of you. And then the other one, we cover it on Thursday. So I think I'll also try to use the breakout sessions so that for the discussions, so that at least I get you guys to practice so that you understand it better. So these are the objectives for today's class. So we'll cover we'll cover the first 3. So on Thursday, we'll cover the Arduino, and we'll cover 2 things on Thursday. That is the Arduino and the Node-RED. So Node-RED is a tool that you can use to virtually simulate an IoT system. So I want to give you a tutorial on how to install it, and so that you can start familiarizing yourself with it before we actually start using it. So that one we'll do on Thursday. So for today's class, we'll cover the first 3. So the basic characteristics and components of system on chips, SoC. Then we'll introduce instruction sets. So for you guys to just understand how microprocessors work. And then we'll also cover models of computation. So we'll just cover these 3. They are broad, so, and a little bit requires a little bit of thinking for you to understand. But we'll cover the first 3, then the last one we'll cover on Thursday. So I think we'll start with what is a processor. Okay. So this is just a general definition of a processor. So it's a unit, okay, or a component that takes in inputs, works on the input, and then produces an output. Okay. So for you guys, you'll be designing embedded systems or IoT systems. You need to understand the different processors and which one are most suited for which types of application, or very shown on this. So I'm sure you've come across this. So this is the architecture, nothing new. So it has the 3 parts: the ALU, the control unit, and the memory unit. So the control unit, it controls operations and communication between the ALU and the memory unit. Then you have the memory unit, which stores data or instructions. Then you have the ALU, arithmetic and logic unit, which does the arithmetic operations and any other complex operation. So the computer will get the input, send it to the memory or the ALU for processing. Then once it gets the output, it sends it to the output unit. It could be a mouse, monitor, whatever it is, actuator, whatever it is you're using as the output. So this is the processor architecture, nothing new. So it's just the same. So I just put it here so that at least you familiarize yourself with it. Then we can classify processors into 2 main groups. So purpose. So last week we were talking of different types of systems. We talked of the general purpose system. We talked of the general computing system and the embedded computing system of its use. So if it's a general purpose, then it's a general purpose processor. If it's for a specific application, then it's an application specific processor. So as you can guess, again, general purpose can be used to achieve so many tasks. Okay, and the specific can only be used to achieve a specific task that it's designed to achieve. Then you can also classify them according to size. So the small processors, then the medium, and then the large and the very large. So the more the gates or the more the transistors it has, the more capable it is. So for example, the VLSI can perform much faster than the small scale processor. Okay. So these are different types of processors. We have microprocessors, microcontrollers, digital signal processors, media processors, and many others. But our focus in this unit will be just two. So we want to look at the microprocessor and the microcontroller. So that is our focus. We won't focus on any other processor. We want to just focus on these two. What is a microprocessor and what is a microcontroller? So for this topic, if you forget anything, please, by the end of this class, make sure you're able to differentiate a microprocessor from a microcontroller. So try to pay close attention when we come to differentiating them so that at least you know the difference between a microprocessor and a microcontroller. So we'll start with a microprocessor. So what is a microprocessor? Okay, so this is a definition. So it's a very large scale integration programmable chip that contains a CPU. Okay, so it has three basic characteristics. So there is the instruction set, there is the bandwidth, and there is the clock speed. Pay close attention to these three things because we are going to have questions around these three. So the instruction set, this is just the set of instructions. So this defines the language that the microprocessor uses. So different processors might use different languages. So the instruction set. So it's just like maybe in a layman's language, maybe if you have maybe a program that only runs on Java, so its instruction set for that program will be Java. If you have another program running on C, then the instruction set will be C. So instruction set is just the language that the microprocessor understands. Okay. So in a layman's language, that is what an instruction set is. Then the bandwidth. So bandwidth is the number of bits that can be processed in a single instruction. Okay. So if you have, for example, a 16-bit processor, it means it can process 16 bits of. So if instruction is 32 bits, it means it can process that at once. It has to break it into two. Hope it's making sense, yeah? So the size of the instruction. So what is the length or the size of the instruction that CPU can process in one go? So a 32-bit processor can process 32 bits of instructions in one go. A 64-bit processor can process 64 bits of instruction in one go. So that is bandwidth. Then there is clock speed. So this is the number of instructions the processor can execute per second. Okay, so don't confuse bandwidth and clock speed. So bandwidth is the size of the instructions. Then clock speed is how many instructions the processor can execute per second. So, for example, a 1 hertz. So hertz. Sorry, for example, don't know if I can need something to write. So for example, a 1 hertz processor, 1 hertz. So 1 hertz should be, it's equivalent to 1 second, right? So that processor can process one instruction in 1 second. Okay. Don't know if it's making sense. Okay, so back to this one. So don't confuse clock speed and bandwidth. So clock speed is how many instructions can the processor execute per second. So if it's megahertz, you have to. So for example, a 1 megahertz microprocessor, it means it can process 1 over can process 1 over the speed. Anyway, there will be an example. We'll see how it works. Okay. So don't confuse the two. So there's the instruction. So here we'll just classify the instruction set. Later in the slides, we'll go deeper into describing how an instruction set looks like. So there are two main instruction sets. So there's the RISC and the CISC. Okay, reduced instruction set computer and complex instruction set computer. So today's class, if I can just reiterate again, we'll focus more on differentiating a microprocessor from a microcontroller, and number two, differentiating RISC from CISC. You realize that most of the things that I'll discuss will either be on differentiating a microprocessor and a microcontroller, or will either be on differentiating RISC from CISC. So pay close attention to these two things. Okay. So so what is so just before we discuss what the two, because they'll be based on these three factors. So what makes a processor fast? So that is in general the time taken for a processor to complete a program. So a program is a set of instructions. Okay, so a program can have maybe 10 lines of instructions, or maybe each instruction is 8 bits long. Hope I'm not losing any of you. So how fast? So it's based on these three factors. So it's I'm not recording. Just record. Okay, I needed to record. So okay, I'll go back to slides. Okay. So I hope you guys are recording your own videos. Like I had forgotten to record. So what determines the speed of the processor? So it's the number of instructions in the program. So for example, if the program has 10 instructions and another one has 100 instructions, then the one instructions will be executed faster. Okay, so that's an easy one. Then the average number of clock cycles. So the clock speed, basically. So for example, a 10 megahertz CPU and a 1000 megahertz CPU, the 1000 megahertz CPU is faster than the 10 megahertz, okay? Because the 1000 can process more instructions in 1 second than the 10 megahertz. No. I think I've confused. That point is the last one, the clock cycle. The second one is the basically. So for example, yeah, this one is more of related to bandwidth. Okay, so for example, an 8-bit processor, if you have an instruction that is maybe 16-bit, then an 8-bit processor will require 2 cycles to execute that instruction. But a 16-bit processor will just require 1 cycle to execute it. Okay, but that is how to explain it. So when you come to risk and CSQ, you'll see that the second point is what majorly differentiates the two. So I want you to pay close attention to what is risk and what is CSQ, and then you'll see that this second point, the average number of clock cycles required to execute an instruction, is what basically differentiates the two of them. Okay. So let's start. It just wants to reduce the number of instructions that the CPU can execute, make the CPU do as little as possible for every cycle until the program is done. Okay. So simple instructions. Okay. So it just tries to minimize the number of clock cycles required to execute an instruction. Okay. So are you now able to record? Okay, so maybe I need to, so give me just 2 minutes. I look if there's anything I need to do. Oh, anyway, I don't know how to set this thing up. Preferences, maybe, I don't know. Audio, recording. Okay, what I'll do is I think if I think you should be able to, because I don't see anything preventing it. I'll share the recording. Maybe we look at a way of sharing that recording, and then yeah, because I don't know how to. Or does anyone know how to set the preferences? I don't see anywhere. I need to maybe change. Uh, okay, so I think I'll share the recording. I don't know if there's anyone who can record, but I'll try to share the recording. Okay, so someone is recording, so I think I can just continue. Okay. Okay. So where was I? Okay. So risk. So pay close attention. So so risk, what it does is it reduces the number of clock cycles required to execute an instruction. Okay. So in a layman's language, what that means is if you have maybe an 8-bit processor, And then you have an instruction set that has maybe the instruction set is 16-bit per line. Then the RISC strategy will make sure that it breaks down every instruction into 8 bits, 8 bits, 8 bits. Okay, so that the program, as it feeds into the processor, it doesn't feed the instructions as 16 bits. Okay, so it feeds in into the processor as 8 bits, 8 bits, 8 bits, 8 bits. It's number of clock cycles required to execute an instruction. Okay, so to differentiate, maybe you might get confused. Is there's something called an instruction and a program. Maybe I'm using two interchangeably, or maybe you just might not be you haven't paid close attention to it. So so there's when I say instruction, this is just the input to CPU. Okay, then a program is a set or okay of instructions. Okay, so a program may have like 10 or 1,000 instructions. Okay, so these instructions need to be fed into the CPU one by one. So what the RISC does is that it makes sure that each instruction is the size of the bandwidth of the CPU. Okay, so that it's executed in one clock cycle. Okay, so it makes sure that as it's compiling this program, it makes sure that the instructions are sequentially arranged into sizes that the CPU can execute in one go. Okay, I hope that's clear. So we go to CISC. Okay, so CISC. So this is a complex instruction set. Okay, so this one focuses on shortening the program. Okay, so if it's shortening the program, it means one instruction might be bigger than the bandwidth of the CPU. So for example, if you have the program having maybe, if it was the program had 100 lines in the RISC strategy, if you apply the CISC to it, maybe it will reduce those lines to maybe 5. Okay, so it shortens the program. So that means the instruction that will be going into the CPU will be bigger, might be bigger than the bandwidth of the CPU. So that means the CPU will need maybe 1 or 2 or even maybe 10 clock cycles to execute one instruction. The question you should be asking is, what is this thing that is maybe modifying the program to maybe a RISC strategy or a CISC strategy? Okay, so you have heard of a compiler, so that is the work of the compiler. Okay, so if this compiler is using a RISC, when you're writing it, maybe it has let's say 5 lines of code. Okay, so if you use a compiler that is based on a RISC strategy, it will break that program into a bigger program, so that maybe it will have maybe 100 lines of code. If you use a compiler that uses CISC strategy, it will break the program into maybe even a smaller program, so that it has less instructions. Okay, so as you can guess, for the RISC, you can use a very small scale processor to achieve whatever task you want, because as you can see, it requires very little bandwidth. So that means the processor doesn't have to be very powerful. Okay, but for CISC, it means you need a very powerful processor to achieve it. because it requires that the processor might need memory to store, because if one instruction is maybe 10 clock cycles, it might need memory to store some parts of the instruction before it actually completes. Okay. So if I was to draw a flow chart, this is how the RISC will look like. So it will just have the instruction set, okay, and then it's executed the way it is, yeah, because it's the size of the bandwidth. But if you're applying CISC, it means the instruction sets have to be. So once it enters the CPU, since it will do more than one cycle, it has to be converted into the bandwidth. So it has to be broken down further into the CPU bandwidth. So you have microcode conversion, then you have micro instructions, then you execute the micro instructions. So if you have 10 micro instructions, you'll have 10 cycles to execute just one machine instruction. Okay, so one machine instruction can be broken down into maybe 10 micro instructions. I hope it's making sense. Yeah? So that is the main difference between RISC and CISC. So I've tried to explain as low as possible, try to demonstrate so that you guys at least get it. Okay. So these are just further explanations. Maybe I've alluded to them or maybe not. So RISC requires few clock cycles per instruction. Okay. So one way of remembering this is RISC requires few clock cycles per instruction. Okay. Then CISC requires few okay. So but due to the large, so that means if you are employing RISC, you'll need a complex compiler, but a simple processor. So that is the trade-in, okay? You employ the RISC strategy, you have a very powerful compiler, but a very simple processor. Because now the compiler will have to do a lot of the breaking down of the instruction to what is manageable for the processor. Now you employ a CISC, it means the trade-off will be you have a very powerful processor, but a very simple compiler, okay? Because the compiler doesn't have to do much, because the micro instructions will be done at the CPU level, okay? So we have these two questions. Okay. So we have these two questions. So write them down. Write them down, write them down. Write them down. Breakout session here so that you guys try to, I'll give you 15 minutes to ask the answers and then we discuss it together. I see if you guys understood anything. So let me just create the breakout sessions. Where is it? Breakout rooms. So there's, I want it to be automatic. Caesar, Dennis, Joanne, Lewis. So just take a few minutes, discuss this. I'll give you 15 minutes plus.
Hello. Hello, do you have the question? Okay, can you share it? Okay.
So anyone who will volunteer? You can raise your hand or yeah. Okay, Timothy.
It is risk.
It is risk.
Yeah,
Why risk?
because there's no need to compile the instruction sets. They just get processed at the processor.
Okay.
Something like that. I'm not sure.
Okay. Okay, that's good. Anyone else? Any group that chose CISC? Okay, so yes, Mombali. Okay, so I think the answer is CISC. I don't know if there is any group that chose CISC. The answer is CISC. Okay. Yes, Yasin.
Okay, we chose CISC because if a program has very many instructions, CISC would reduce the number of instructions to execute that program. Hence, it would maximize on the speed.
Yeah, because I want you guys to remember that breaking down the instruction sets breaking down the instruction set into smaller bits does not increase execution time. Okay, so if a program, let's say, has originally has maybe 10 lines of code, then you break it down into 20 or 50, that doesn't reduce the execution time. But on the contrary, if you reduce it to maybe a 5, it will reduce. But again, you can come up with the arguments that what if the CPU is faster? Then yeah, that's a valid argument. But mostly CISC processors are more powerful than RISC. So still the argument will be in the favor of CISC. Okay. The second one, to minimize the development cost and sale price. Anyone who wants to try? Yes, Raj.
We chose risk for that, reducing development cost and sale price.
So why is
Because
that?
because RISC helps reducing the number of cycles per instruction. Therefore, it's less strenuous on the hardware. Therefore, you can implement low-end hardware and still achieve the task. Therefore, minimizing the development cost.
Okay, so that's okay. So I don't need to add anything to that. So Raj is what Raja said is correct. Then the second one is which processor will you use to perform, will have a built-in ability to calculate the square root instead of having the compiler write long machine instructions. I think that question is leading, but anyway, yes, Waweru?
So for this, our group chose CISC because it's a complex processor, meaning that it must have the capability to calculate square roots based on the hardware, inbuilt in the hardware, compared to RISC, which has it on the software side. So it, for RISC, it would have to come up with long machine instructions to calculate the square root instead of RISC, which has it inbuilt.
Okay. I don't need to add anything to what already was said, so that is correct. It's true. So Anthony is asking a question: is the time needed to execute one instruction in CISC and RISC the same? That depends on the microprocessor you're using. Remember, we are dealing with two things here. Yeah? So you can have a microprocessor, maybe 16-bit processor, but the strategy you use, the microprocessor can use either. Okay, so it can choose to use RISC or CISC. Okay, so the time taken for one instruction depends on the processor. Okay, so if it's a 16-bit processor, then yeah, depends on the processor. Yeah? So the strategy is what we are talking about in this exercise. Okay, so we continue. So the next thing we cover is the microcontroller. So we've been covering the microprocessor. Now it's the microcontroller. So what is a microcontroller? So this is the formal definition of a microcontroller. So a device that controls the transfer of data from a computer to a peripheral device and vice versa. So that is a controller. Then a microcontroller is now a VLSI unit, a very large scale integration unit that contains all the components comprising a controller. Okay, so what are these components? So a controller has a CPU, it has RAM, it has ROM, it has input output ports, it has timers. Okay. Remember, for the microprocessor, it had only 3 parts, and those 3 parts were inside a CPU. So in short, what am I trying to say? And peripheral devices. Okay. So RAM, input output ports, timers. Okay. So if you compare a microcontroller and a microprocessor, so on the left, so a single chip, very large scale, okay, and inside there is a CPU. So CPU is CPU, memory, input, other devices, okay. For a microprocessor, it's can be very large scale also, but inside it's only CPUs. Can be one, it can be many, okay. So what is the conclusion? So you need to differentiate between a general purpose computer and a microcontroller. Okay, so general purpose are designed to perform so many tasks. A microcontroller is designed to perform a specific task. Okay, so you'll see these by the time this ends, or by the time this class ends, you'll be able to see some of the application areas of microcontrollers. Maybe some of you already know, or you have examples of microcontrollers, but if not, we'll cover it on Thursday. Okay, so Arduino is an example of a microcontroller. Let me just put it out there. Then a microprocessor, okay. So on its own, it's difficult for it to exist on its own. Yeah, so it has to be attached to a computer or something else. Yeah, but a microcontroller can exist on its own and perform a specific task. Yeah, microprocessor, not really. Okay, you need to just be either inside a computer or maybe a device. Okay, so that is the conclusions. Yeah, takeaways. Which microprocessor is more powerful? A 32-bit microprocessor that runs at 50 megahertz or a 16-bit microprocessor that runs at 25 megahertz? Anyone? Yes, James? Anyone with an idea? Which one is faster? So this one goes back to the first slides that I was explaining. So you remember there were three things you needed to consider: instruction set, bandwidth, and clock cycle. So here what you have? You have the bandwidth. So one is 32 bits, the other one is 16 bit. What else do you have? You have the clock cycle. One is 50 megahertz, the other one is 25 megahertz. Okay. So in 1 second, the 50 megahertz can process how many instructions? And then in 1 second, the 25 megahertz can process how many instructions? Okay. Then what is the size of instruction that the 50 megahertz can perform per cycle? So it's 32 bits. The other one is 16 bit. So I think I've tried to explain it. So which one is faster, or which one is more powerful? Yes, Stacy?
I think the 32-bit microprocessor with the 50 megahertz is more powerful.
Why is that?
This is because, first of all, it's 32-bit, meaning that it has a higher bandwidth, which means that even for complex instructions that are larger, it doesn't have to break them down like the 16-bit microprocessor would. So it has about 50 megahertz. It means that it has a higher clock speed, which means that more clock cycles per second, which would mean that more instructions are being processed per second, which would make it more powerful.
Okay, sawa sawa. So I don't need to add anything to what Stacy has explained. So I hope it's clear to everyone. I hope it's making sense. Yeah. The second one is what is the difference between a microprocessor and a CPU? So what is the difference between a microprocessor and a CPU? Yes, Madenge?
I have a question about the previous question. Yeah. What
Yeah.
if you had a 32-bit processor that runs at 25 megahertz and a 16-bit processor that runs at 50 megahertz?
Yeah, they will be the same.
They'll be the same. Okay.
Yes, yes. So, the second question, anyone with an answer? This one I haven't explained, so I want to see if you guys can figure it out. Anyone who has figured it out? The difference between a microprocessor and a CPU. Anyway. Yes, Isaac?
Okay.
Okay, I think CPU is the part of a computer that actually executes instructions.
Mhm.
But now a microprocessor is now a single chip implementation of a CPU.
Mhm.
Yeah.
Also,
But ideally, I feel like it can be used synonymously.
mhm. Yeah,
Yes.
yeah. People use it synonymously, but they're different.
Uh-huh.
So maybe if I can ask it more directly, which one is inside the other?
A CPU, a microprocessor is a single chip implementation of a CPU. So it means that the inside the microprocessor there's a CPU.
Yeah. So what I'm trying to ask, so the answer to this question will actually give you hints to the next two questions. Okay. So a microprocessor has one or more CPUs. Yeah. So I think that is if you want to be very direct, then a microprocessor uh, is composed of one or more CPUs. Okay. Then the third one, can a microprocessor multitask? Anyone wants to try? I think that's an easy one. Yes, Macharia.
So yeah, it can be the idea that it can contain one or more CPUs explains that it can.
It can multitask, yeah. Now, for this third one, I want you guys to do some little homework. So yes, it can multitask, but there are two main ways of multitasking. So one is called concurrency. So just write that one down. Concurrency, it has to do with the interrupt control. Okay. Then the other one is parallel computing. Parallel computing. So during your free time, try to differentiate the two. So what is concurrency processing and what is parallel computing? Then lastly, a microcontroller cannot multitask. True or false? Anyone with an answer or wants to try? Anyone? Okay, so no one wants to try. So we'll move on to the next thing, the last bit, instruction set. So this is just, so what is, so in the first few slides we talked about, we mentioned instruction sets and tried to classify them as a RISC or CISC. But here now, we're trying to sort of describe how it looks like or how they operate, okay? So what is an instruction set? What is it composed of? Okay, so it's composed of two things: the opcodes, which is an assembly language, and the native command. Okay, for a particular processor. So different processors might have different commands. Okay, so the same way we humans have different languages, we can do the same task, but we understand it differently. Yeah? So it's the same with the microprocessor. There's some that use a different language from another. So, for example, down here we have an instruction set. So you have the operation here, the op, and then you have the operand here. Okay, so you have the operation and the operand. Okay, so to maybe describe it much faster, so you can have instruction sets that can perform three main tasks. So there is data transfer, There is a flow control and there is arithmetic and logic. So for data transfer, for example, this is an example of an instruction set. So you have an opcode, then the operand. So for example, move dx, cx. So move is the opcode, then dx, cx is the operand. Yeah. So you're basically saying move move the contents that are in register cx to dx. Okay. For example, move CL to 03H. So move this value here into this memory. So if this memory, so ideally, if this memory is a display, then the user will see 03. If it's the ALU, then the ALU will get a variable of 03. So it depends which location are you moving it to. So registers are meant for input, output, memory. Okay. So the output, for example, your video, it has a memory that once the control unit puts something there, then you'll be able to see it. I don't know whether it's making sense. Then you have flow control. So these ones are the ones you use when you're writing a program. So for example, for you, maybe you can just write an if else, but you don't know how it is decoded into a microprocessor language. So these are examples. There are many. Okay, so there's jump, branch. Branch is an if else, yeah. If then repeat until is a while loop that is written down into the assembly language. Okay. Then the arithmetic. So I don't know if you've done digital logic, but usually no processor can do, what is it called? Subtraction. There's no processor can do subtraction. So so if you do maybe 3 minus 1, your processor has to use different operators to achieve that task. The thing is, they are so fast to think they actually do the subtraction, but there is no way zeros and ones can be subtracted. I don't know how to explain it, but there's no plus or minus. Okay, there's only plus, so there's no minus. So the minus operations have to be modified so that there's a way it does it. So there's using the shift and rotate, it can achieve subtraction, but it's not direct. Okay, so these are operations that for the arithmetic. So all these, for example, I haven't just put them into the structure of opcode and operand, but all these have a structure of the opcode and operand. Okay. So this is the end of today. So this is the end of today's class. What to discuss, I think you already know the answers. So the circuit in the previous slide, and then the components that make up a CPU, the memory unit, control unit, and so forth. Yeah. So this is just meant to help you understand. So I hope you now can tell the difference between a microprocessor and okay. So that is the end of today's class. So we meet on Thursday. We'll cover two things on Thursday. This is the Arduino microcontroller and the Node-REDs and what you can use it for. Okay. So any quick questions? I think we can stop here for today. So you guys have a wonderful day and obey the guidelines of Mutaikagwe and stay safe with your movements. Okay. See you on Thursday.